So today we will have a presentation by Arias-Castro, who's a professor at the University of California, San Diego. Thus, today's seminar was at 6 p.m. in France to avoid Ari doing a presentation during the night. And Ari will present some of his work on the estimation of distance, geodesic distance, and application to positioning and manifold learning. So, Ari, yes, you can go ahead for your presentation, and thank you very much.
Thank you for the invitation. So I changed the title a little bit because of a newer project I'll talk about down the line that actually relates to some of your work at INRIA. Okay, so I'm going to present a few projects, and here are the collaborators on all those projects. So I'm going to start with estimating positions from distances, which of course is a very classical problem in not only statistics, but also in other areas in engineering, for example, and in applied mathematics, and also pure mathematics, as a matter of fact. So there are different names for it. I'm going to use graph embedding for now. So the basic problem is that we have a graph, a weighted graph typically. Actually, towards the end, I'll talk about the situation in which the graph is not weighted. But let's just imagine we have a weighted graph, and so the node set is V, the edge set is E, and then the weight function is delta. So delta ij is the weight between I and j if there's an edge between I and j. All right, so we provide with the weighted graph and an embedding dimension, and we want to find, we essentially want to so-called embed the graph in RD. Okay, so that means that to each node we associate a point in RD, and we're going to denote those points by y1 through yn. There are n nodes corresponding to endpoints. Okay? And the idea, vaguely speaking, is to output points such that their pairwise Euclidean distances are approximately the corresponding weights that we're provided with. Okay, so for example, this is one of the classical approaches, which is via what's in statistics called the stress or stress function. And it's essentially what you would think of doing first, which is essentially using the error sum of squares and minimizing that if at all possible. And the problem that results from this is not convex, and it's not easy to solve. And people have used techniques that are somewhat well known in optimization, such as measurization. That's what, for example, Smakov does. It's one of the well-known algorithms for doing this. I'll talk about another method very soon. So as I said at the beginning, graph embedding is a problem that's well known and has multiple names in different areas. In statistics, it's called multidimensional scaling. And then there are other names such as graph drawing, graph realization, Euclidean distance matrix completion, sensor network localization in engineering, and so on. There are important connections to nearest neighbor search, embedding of finite metric spaces, and manifold learning. I'll talk about manifold learning later on. All right, so the second method I want to mention in a bit more detail, because some of the work I'm presenting here relates to that, is classical scaling, which dates back to the 1950s. And it actually it approaches the situation not through the stress function that I showed you earlier, but through a different one I'm not showing here. And it attempts to find a solution via a eigenvalue problem. And what we did recently is to actually look at the situation in which the similarities are not known exactly, but with noise. They're only available with noise. So in principle, the problem would be solvable exactly if there were no noise, but there is noise. And the question was, how stable is classical scaling to noise? And it turns out that it is stable. There was prior work dating back to at least the 1970s on the problem, and a bit more recently by some of the two authors that worked on isomap actually. And what they did was obtain the Taylor developments. And what we do is, in the recent work, is derive a perturbation bound, like the ones that are available for, like eigenspaces such as the Davis-Kahan sine theta theorem. So we do something like that we obtain the perturbation band like that one. I'm not going to show it to you. It's a bit complicated, but actually it might be, it's in the next one. I'll go very fast on it, but we obtain something like that for classical scaling. I want to make sure that people are hearing me. Are you hearing me okay? Anybody?
Yes, we are.
Okay, great.
Yes.
Because I'm not getting any feedback, so that's okay, great. So I'm just continuing. So here's the bound. I mean, it's a bit complicated. The point being that, so anyway, you can perhaps look at the slide here, but it's what we do is more or less, if you know the Davis-Kahan sine theta theorem, which is one of the best known perturbation bounds, in that case for eigenspaces, we obtain a perturbation bound for classical scaling in the sense that if the distances are observed with some noise, then we obtain so a classical scaling outputs a point set that's close to the true point set. Of course, the true point set is not available because we only have pairwise distances, but I'm talking about up to a rigid transformation, and we have an actual bound which relates to how much noise there is in those distances we start with. Okay. It turns out that there's also we argue that the bound we have is optimal in rate as well. Probably not the constants, but the rates. All right. So okay. So moving on to, so this is when the matrix of pairwise distances is complete, and I started talking about graph embedding. So it's when the graph is complete. What happens when the graph is not complete? Meaning when the similarities are missing. Well, in that case, we cannot use classical scaling. We have to do something else. And it's a situation that people have studied for quite a few years, in fact. In pure math, there's this question of whether a graph can be embedded uniquely. And the theory that sort of studies that is sometimes called rigidity theory, although that name is also used in other contexts in math. But there's something like that for this particular problem, and it dates back to the 70s as well, actually. Although classical scaling dates back to the 1950s, so even earlier. All right, so many methods have been proposed for multidimensional scaling when some of the dissimilarities are missing, and even when the dissimilarities are not missing, and we actually saw two of them. There are others, I'm sure. But anyway, now the general case where some of the dissimilarities may be missing. So the simplest method, and also the one I will be focusing on in this presentation, is graph distances. So remember, what we have can be the data we have can be represented as a weighted graph, and it's tempting when some of the distances are missing to fill them in using graph distances. It's very simple, relatively fast, computationally speaking, and that's also a method that's perhaps one of the oldest for completing a dissimilarity matrix. It dates back to at least early 1980s with the work of Kruskal and theory here in 1980. And then, of course, if you want to actually get an embedding, then you can, once this matrix is completed, you can apply classical scaling or any other method that works when, or that can be applied when the dissimilarity matrix is complete. Yes, that's just one method. There are other ones. This one is a pretty greedy one, in which a clique, or in more generally a subgraph that's rigid, in the sense I mentioned earlier, is embedded, for which all the pairwise distances are available. I guess that's because we're saying, because I'm talking about the subgraph here. So anyway, we can talk about the clique, which is the simplest one. So so it's a subgraph with all the pairwise distances are available. And in that case, we know we can apply classical scaling. So we do that to embed the corresponding nodes, and then we sequentially trilateralize the other nodes. So that's a method that has been proposed, quite greedy in nature, as you can imagine. Then there's one that's also working with cliques, but or again more generally with rigid subgraphs, for which well, yeah. But anyway, let's talk about cliques. So you can embed, say, all cliques, or in principle, you don't have to embed all of them, but they have to have them so that there is enough overlap that that you can go from one to the other, and also that they cover the entire graph. Okay, once you have, so each of those cliques you can embed by classical scaling, and in principle, you embed them in parallel universes, as if so parallel copies of RD. And yeah, if you want just one map, right, you need to synchronize them. Sorry, one embedding. That's what I mean by that. You need to synchronize them, also call align them or register them, and that there's a bunch of work in that area. I already mentioned Smakoff. So Smakoff can be applied when some of this is missing. In fact, the formulation I have earlier in the slides actually is one where some of the distances can be missing. And there's also SEP or semi-infinite program relaxations that people have suggested for this problem. Okay, so I'm going to focus on graph distances as a way of completing the similarity matrix. And again, from there you can obtain point sets by simply applying, for example, classical scaling. So graph distances, the situation is very simple, and here's a situation that sort of illustrates why you can expect it to work in some situations. So here's a point set. You don't have available the point set. Imagine you only have available the distances between points that are linked by an edge here. Okay, so this I generated as a random geometry graph. So I just sample some points uniformly at random in some rectangle in the plane, and then I I connect 2 points within all the pairs of points that are within a certain distance. That's how I generated this point set. And just imagine you don't have the points; you only have the pairwise distances for points that are within a certain distance. Okay. Okay. And this is what you would do. So imagine you want to compute the distance between the two endpoints there that are depicted as red squares. And this is the method. The method is, so the distance between those 2 points is not directly available because there's no black edge between them, as you can see. So what you can do is use as a proxy the graph distance between those 2 points. And that's effectively how you estimate their pairwise distance in this method. And of course, the truth is this purple line instead. So now imagine that you could, I don't have it here, but you could imagine like a sample that's a bit finer. You would see that the red line becomes closer and closer to the purple line. This is actually very easy to prove, and that's exactly what's going on. Okay, but let's look into that in more detail. And there are connections, interesting connections to manifold learning that are coming up. So, okay, so just a reminder what graph distances are. So remember the weights are the deltas. Here I use, instead of subscripts, I use it as a function, same thing. And so the graph distance between nodes I and j is simply the infimum over chains that link so-called I and j. And along that chain, or so-called typically called path, we just sum the weights of the edges. So if one of them is infinite, which would be the case if the delta there is missing, then we will have an infinite sum here. So we only go over paths that's really, I mean, true paths, the ones that really are a sequence of edges in the graph, existing edges in the graph. Okay, in principle, you can go over all possible chains. Okay, that's what delta ij is, a big delta ij. And then, so let's visualize this to our ball neighborhood graphs. So again, we want to link this. We want to understand what's going on when the graph is embeddable, because otherwise all things are, it's hard to, in a sense, come up with a general result. So let's talk about the situation in which the embedding is possible, and we only have available to us the smallest distances, and the pairwise distances specifically that are less than or equal to r. Okay, so in other words, we have a point set that's unknown to us, x1 through xn, that's already in a sense embedding the graph perfectly. And delta ij is the pairwise distance between xi and xj, but it's only available to us if it's less than or equal to r. Otherwise, you can say it's either not available or same thing, infinite. Okay. Right. So we have a little lemma in this same paper. The main contribution of the paper is the result I showed you earlier, very briefly, that of a perturbation bound for classical scaling. In that same paper, we derive a perturbation bound for classical scaling. We get, I'm not showing it to you here, but what we get is a performance bound for isomap. Isomap being one of the main methods for manifold learning, and it uses classical scaling crucially. So that's why we were able to transport, in a sense, the perturbation bound for classical scaling into effectively an error bound for isomap. Okay. And in the process of doing that, we refined an existing bound. I'm going to talk about it on how well the graph distances approach the actual Euclidean distances. So here's a little lemma or a little proposition. So the point set is x1 through xn, and epsilon is the density of that point set in its convex hall. Okay, so conv here of x is a convex hall of x, and epsilon is measuring how dense the point set is in its own convex hall. Okay. In other words, epsilon is going to be small when essentially x1 to xn is a fine sample of a convex domain in RD. And that's when the graph distances are going to work well. Otherwise, we'll see later, if there is a hole or the set is just not convex, then the graph distances won't do too well. They will estimate the intrinsic distances, but not the Euclidean distance, which of course the two are different when the domain is not convex. All right, anyway, so here, just have in mind a situation in which this is a sample from a convex domain, but in any case, epsilon here is going to be small in that situation. Remember this parameter r, which is actually not a parameter. Well, it is a parameter in a sense, but we don't have it's not a Turing parameter. It's not something that we have access to. Okay, but anyway, so it's provided to us with the data. If epsilon is small compared to that r, then the graph distances are bound from above, so they're they're bound from above the Euclidean distances. In other words, the Euclidean distances are less than or equal to graph distances. This is because in the Euclidean space, of course, the short path between 2 points is a straight line or line segment. So this is trivial, and the upper bound here, again, it's not hard, but it's you have to do something for it. Is well bound also by the pairwise distances, but there's a factor in essentially the error is proportionally in epsilon over r squared, and that was our improvement. We went from epsilon over r to epsilon over r squared. So there were a couple of people that did that before us, in particular Bernstein and others. Those are the isomap people that had, in the process of examining how isomap was behaving, they proved essentially the same bound, well, the same upper bound, except that it was epsilon over r as opposed to epsilon over r squared. And a few years later, another group actually proved essentially the same bound that Bernstein had before, but in the context of so Bernstein did that in the context of manifold learning, and Montanari and Carbasi, they did that in the context of a flat domain, actually a flat convex domain. In fact. So more on isomap later on. Right. So building on into more somewhat complex situations. Now we are, instead of being in a convex domain, we're going to talk about points on the surface, in particular, in principle, a curved surface, and the goal is to estimate the pairwise distances again. Okay. So this is even closer to manifold learning now, because we're going to assume that the points are given to us, not just the pairwise distances, but the points are given to us. But we don't know the distance, we don't know the underlying surface, and nonetheless, our goal is to estimate the pairwise distances on the surface. So those are sometimes called intrinsic distances. And yeah, so at least from the point of view of manifold learning, if you look at the two important methods, isomap in particular, and also maximum variance of folding, both of them intrinsically use pairwise distances. So there would be an interest, just from the perspective of manifold learning, to study that problem. And it's also true in motion planning if, say, the robot, whatever is moving, moves on the curved surface. And the surface is known through a sample of the surface. All right, so suppose we have a subset. In principle, for us, it's going to be a submanifold. And the intrinsic distance on a subset is simply, if you take 2 points on the surface, or set x and x prime, then it's the length of the shortest path on that set, or in that set, that connects those 2 points. So we don't know the surface or set, we only have a sample of points on the surface. I'm not assuming any randomness here or any sampling distribution. I'm going to reason the way I did before, which is in terms of how dense the point set is in the set on the surface. All right, so so we have a point set x1 to xn on that surface. The surface is assumed to be compact and connected for now. We're going to see more later. And the goal is to estimate the pairwise distances between those points. Remember, G here is defined as the intrinsic metric on that set. Okay. So our technique here, so now R is going to be a tuning parameter. So we form the R ball neighborhood graph based on those points, meaning that we consider the graph whose nodes represent the points, and the edges are defined between points or nodes such that the corresponding points are within distance R. Okay. All right, and then it's also weighted by the corresponding Euclidean distances. All right, so delta as before, but now I'm using x and x prime, but delta is the graph distance in the corresponding graph. Okay, it more or less has the same meaning as before. It quantifies how dense the point set is, but now on the surface as opposed to its own convex set. And in the same paper, Bernstein and others, they obtained then, so if you remember this bound here. Okay, so they have an upper bound, so they're bounding here delta by the actual distance. And here they're doing the same thing, but in a curved situation. And that's what I was saying before. So here they don't have a square, or we have a square, even in the curved situation, if, well, in a particular, very, very special situation I'll mention later. Yeah, so they get this bound. Again, this is in the curved situation, at least in principle. And there is a corresponding, I guess, depends on how you see it in terms of G or delta, but so here we are upper bounding delta by something like 1 plus a small error times the intrinsic distance. And here we're doing the other way around. So we bound the intrinsic distance by something 1 plus something like an error times the graph distance on the R ball neighborhood graph. Okay. And so one of them, let's be sure here. So one of them is in a tunnel over R. The other one is in R squared. That was the result. In the paper with Thibault Leguic, what we did was we took time. So we looked at this and then also pushed it further. We took time to revisit this result and obtained it with a slightly worse constants, actually a couple of constants, based on similar work of Dubin's on motion planning, effectively on looking at shortest length curves with a curvature constraint. And that's exactly what you need in the context, in this particular context, because you're looking at intrinsic distance on the surface, and here the surface is assumed to be essentially smooth because we assume that the shortest paths on S have curvature bounded by kappa. Okay, so S in principle here can be something other than the manifold, can be possibly stranger, but the shortest paths are very well behaved. And so because of this assumption on the shortest paths on S, what you're bound to do is looking at how much curves with curvature bounded by kappa pointwise, how they behave, and that's exactly how you get an upper bound like this. And that was already studied by Dubin's much earlier in the 1950s. We also saw in the same paper that not only we get, although this was essentially implicit in Bernstein's work already, but we make it a bit more explicit in that what we do is we show that not only we can approximate the pairwise intrinsic distances or the graph distances, but we can also approximate the actual shortest paths by the shortest paths on the graph. Okay, not surprising, but we make it more explicit. Our main contribution to that paper is to go beyond that, which essentially was Bernstein's work earlier than us. Although we do extend some of those results, but our main contribution to that paper is to look at the curvature constrained shortest paths on the surface. So now we measure the, well, let's call it, I don't know if you can call it distance or semi-distance on S between 2 points and x and x prime by the length of the shortest path joining x and x prime that satisfies a curvature bound, and specifically with curvature, pointwise curvature bound by kappa. And kappa here is a parameter that's either fixed by the problem or user chosen. Okay, and okay, so for this, so if we want to use, as we did, the graph distances, now we constrain the paths to have on the graph, see them as polygonal lines and constrain their curvatures. And this is very natural because in a sense, we want to build a plug-in estimator for the pairwise distances with the curvature constraint. And so for this, we needed a notion of curvature that was appropriate. And there are a few that have been proposed for polygonal lines. So of course, the usual definition of curvature will give, it would be essentially zero curvature in the straight parts of the polygonal line and an infinite at the corners, and that's not useful for us. But people have suggested notions of curvature for polygonal lines. And the one we use is essentially 1 over the radius of the circumscribing circle passing through 3 consecutive points. So if you have here the pictures here, this is a polygonal line. We want to say estimate the curvature at this point right here in the middle. And actually not put in the middle because there are 6 of them, and this one here. And so we look at its 2 immediate neighbors and form or compute the circumscribing circle, and then take 1 over that. And that turns out to be a good notion of curvature for us, in the sense that there's a consistency. So if you take a curve that has find curvature. And if you just imagine approximating it by a polygonal line, finer and finer with the points defining the polygonal line being on the curve, then you have a consistency in the sense that the curvature of the computing, as shown here, converges pointwise to the curvature of that curve. Okay, so that's a nice thing to have, obviously. And with much more work, we were able to get a finite. So this is more an asymptotic one. So it's like if you have a curve, a smooth curve, you fix a point on that curve and you approach that point on both sides, then you have the limit I just mentioned. But here this is non-asymptotic in a sense. So if you have a curve and you have again 3 points on that, but the points don't move. If they are within, if they are sufficiently close to each other, so if the two extreme points are x and z here are sufficiently close to each other, of course this is measured in terms of the feature here, the curvature of the curve. Then the discrete curvature, so defined by the triplet x, y, and z. So they are in that order on the curve. So y is between x and z. The discrete curvature, as I just defined it, is bounded by the curvature of the curve. And this is a key result. So for lack of time here, I'm a bit constrained, so I'm going to go fast now, but so I'm just going to say in words what's going on, and actually skip on explaining what on reading the equations. So for technical reasons, we work with an analysis graph instead of a neighborhood graph, instead of a ball graph. So we removed, essentially we work with the corona. So we removed the an inner ball. This is just to regularize the graph. I'm almost sure we're not the first ones to do that sort of thing. But anyway, it simplifies things for us. And then what we simply do is, this I should say, is that we do a plugin. So we estimate the curvature-constrained, kappa curvature-constrained distances on the surface by computing an analysis graph where the radius of connectivity is r still, but we remove inner ball of radius r over 4, for example, something like that. And then we simply compute the pairwise distances in the graph, but we constrain the path to satisfy the same curvature bound with the curvature defined as I did earlier for polygonal lines. Okay, and that's just a plug-in estimate. And then we obtain similar bounds, although with they are somewhat more complex. So we have this upper bound, and it looks exactly the same as before. And then it turns out that instead of a lower bound, what we show is that the paths on the let's see again, if I remember, I don't have it in mind so well. Yeah, that's right. Okay, so without even constraining them, so as long as the surface of course is smooth enough, the unconstrained paths already in the graph, in the analysis graph, actually satisfy a bound on the curvature that's almost what we need. So it's at most kappa prime. With kappa prime is at most some kappa plus an error that's small as long as epsilon over r cube is small. So it's that's going to have to be smaller. But if that's the case, then we almost get what we want, meaning that the unconstrained choice paths are already satisfying some curvature constraint that's close to what we would like. So now we're moving on to a bit of a somewhat more recent project, which was posted in the archives a couple of months ago, but still on estimating pairwise distances on the surface, and then an application to manifold learning. So, summarizing sort of what I showed you, and a tiny bit more. So, in a sense, I don't know if I said everything I'm going to say now, but now. Looking at this very special case where the set S there is a surface that's isometric, to a globally isometric to a convex domain. Okay, so imagine you have as if a piece of paper which is rectangular, so convex, and then you fold it, in 3D. So you pick it up from the table, and then you fold it without stretching the paper or breaking it. Okay, and without also having the paper touch itself. So that's that. And we also assume that you don't, when you do that, you don't do it with kink. So like you let the surface be smooth. In particular, we still assume it to have positive reach. So for those that don't know, I mean, I'm assuming here everybody would know that positive reach essentially means in this context twice differentiable, essentially. Okay. All right. So right. So if we combine the bounds that Bernstein and others got plus the refinement that we got in actually, it's not this paper is another one that I mentioned earlier. So the one with average Alan and Bruno Piltier. Sorry about that. Then what we get, otherwise we don't have the square here. So Bernstein and others, they obtained this, but without the square here, and the square comes from this other work. Sorry, not this paper. So anyway, so we're in the context where we have points on the surface. The surface is isometric to convex domain and has positive reach, and we know that we can get this boundary. And R here is a tuning parameter. So what we have is a point set. We have the x's, and in principle, so in a sense, as if in the machine learning, in the manifold learning situation, and R is a tuning parameter. And so we might as well optimize this. And so in principle, optimizing this would require knowing epsilon, which is not necessarily available to us, although it can itself be estimated. But if we knew epsilon, then we would choose an R so as to optimize the two bounds, and what we would get is that we can get this. So our estimate. So now this is the unconstrained situation. Okay. So the graph distances come close to the intrinsic distances, and the error, the relative error is is of order epsilon. The question, of course, arises whether this is optimal or not. And there's not a lot of very few optimality results really in multidimensional scaling in general, and also in manifold learning for exactly the same as if reason, because the two fields are very closely related. So, and just to be clear, epsilon, what is epsilon here? So it can be almost anything, but if you assume the x's, for example, to be uniformly sampled from the surface, and the surface is of intrinsic dimension k, then epsilon is going to be is known to be on the order of log n over n to the power 1 over k. And even if you place the points yourself by hand and try to make epsilon as small as you can, typically you cannot make it smaller than the same thing but without a log. Okay. So this is just to give you an idea what it will look like in a situation in which you have an IID sample from the surface. The same holds if instead of a uniform distribution, you get a distribution with a positive density on the surface. Okay, so right. So in this case, so this I was saying for S isometric to convex domain. So if that's the case, then it has a boundary. For the usual technical reasons, we assume the surface S now has no boundary, and you assume it to have posterior reach. That's the context of what we're doing. So this is the paper I just mentioned that looks into the optimality of this bound. Okay, that was in a sense available in the literature, at least combining Bernstein's work and the more recent work I mentioned earlier. Not this one. This is by mistake, but it turns out that's not the case. So we can do better. So we can get a relative error of epsilon square as opposed to epsilon. And the key idea, and it turns out that epsilon square is minimax optimal in a certain sense. And it turns out that the key idea is relatively simple. Is instead of using graph distances, is to do refinement of that, which involves reconstructing the surface. So we try to first estimate the surface, and then do a plugin. So estimate the intrinsic distances on S by the intrinsic distances on the estimated surface. So S hat here. S hat should be scripted actually, but anyway. And this works well if S hat is close to S, not to zero order, which would be in Hausdorff distance, but in first order, which is not only in Hausdorff distance, but also in at this orientation. So the tension spaces have to be close to each other as well. And when that's the case, then it works. In the sense, it works in that it provides a bound in epsilon squared. So in the paper, for technical reasons, and it took us a while to absorb, I don't know if we did it very well, but the literature on meshes, and there are some experts in the audience here on this. What we started by doing, to be sure we had it, is we approached it non-constructively by simply essentially defining S hat here as, so if you take the class of surfaces that have the same properties as S, so exactly the same properties as S, so compactly connected manifold weld boundary that goes through all points. Okay, so that forms a class of well sets, and then you take the one among them that has the largest reach pointwise. Okay. Then if that's S hat, then what we show is that S hat satisfies the required approximation properties to actually yield an estimator that has a relative error in epsilon squared. So we do it like this to be sure we have the result, but then we dove into the literature on mesh constructions, and it seems the one that has the most developed theory is the one that is known as the Penrose-Delaunay complex, which provides a mesh, so a piecewise affine surface, and that construction relies on knowledge in principle, on knowledge of the tangent space of the surface, which for us was inconvenient, so we used some other work. So this here I'm referring to a book that came out fairly recently by Jean-Daniel Boissonnat and Frédéric Chazal, and I forgot the first name of this person, but even it. And then we used in conjunction with the results in here, recent results, and we actually crafted for that exact purpose by Eddie Amari and Clément Lebrach for underestimation of tangent spaces. Okay, so here's a cartoon image. Well, actually, it's not quite cartoon because it's actually wasn't on a computer, using actually software developed in part by some of the same people. So we took a torus and then sampled it, and so I think there's three colors. I think the other one is green, is the actual torus path between those 2 points. The blue line is the one that is the torus path on the mesh, which you see reconstructed here. And the red line is the one on the shortest path on the neighborhood graph. So we see that the blue line is much closer to the green line than the red line. And here it's with the finer sample. We have some experiments in the paper. This is with with a student of mine, Alan Cho. Also, it goes by Alan Cho or Fong Cho. And as you can imagine, we thought of going back to manifold learning. Once we have a finer estimate of pairwise distances on the surface, immediately one thinks of isomap. So what we did is propose a variant of isomap, the one you're already thinking about, which is instead of instead of estimating the intrinsic or geodesic distances on the surface using the shortest path distances on the neighborhood graph, what we do is we reconstruct the surface, or attempt to reconstruct the surface using a mesh, and then compute the pairwise distances on the mesh. Once all those distances are available, we apply classical scaling. That's the same as with isomap. So the only thing we changed is the routine in isomap that computes the pairwise or estimates the pairwise distances. And in this case, we use the mesh reconstruction. That's what we call mesh isomap. And we show, we argue, so there's some issues. If you see here, we assume that S doesn't have a boundary, and for isomap, if you can hope it to work, it will be, and same thing for mesh isomap, S will have to be isometric to convex domain. So there's a boundary, and so we argue, hopefully effectively. I'm not sure how well we're doing, but hopefully well. We argue that we can get a finer bound for isomap. So we had one in this paper, as I mentioned, and it was in epsilon, I think. So now we get a bound in epsilon squared for mesh isomap, which we also argue is minimax, which might be the first optimality result in manifold learning, actually. Right, I'm running out of time, so I'm going to have to go very fast. I want to mention a couple of other projects. So so coming out of this notion of, so the work with Thibault Le Gouic on curvature-constrained short path distances and their estimation using graph distances with a curvature constraint on the result on the corresponding polygonal lines. So we looked at using the sort of notion of curvature to generate random paths, so something like a smooth version of Rayleigh motion that looks good, quote unquote. Okay. So this is what I did with Clément Merenfeld, who was at the time a master's student who came to visit me for a few months, a very talented young researcher who is now working with Marc Hoffman at Dauphine. And this is the sort of thing we are able to generate, and we prove some things about it. Most of the work was his, actually. So I won't give you the detail, but it's defining a marker process on the successive angles, and we make them so that there is so we're enforcing a curvature constraint of the sort that I showed you earlier that applies to polygonal lines. And the result is we have what we wanted, which is that we have a random path which, in the limit, sorry, we have a random walk, really, defining a polygonal line, which in the limit is as if well, it gives you this, something like that. This, of course, is discretized, but on the screen it looks pretty smooth now. And it does have a finite curvature with property 1, and we can quantify it. It's a fairly simple process we have at the limit. That was satisfying, and we have also want to mention another project. So this one is with Antoine Chanaron and Bruno Pelletier and Nicolas Verzelen. So I mentioned at the very beginning of the talk, which is that this is a situation in which we have a graph that we also want to embed, but we don't have the weights. So we only have the identity matrix. And what we show is that the graph distances are also possible. I don't have time to do this in detail, but anyway. So we can also use graph distances. And we have an upper bound on how well they perform, and you recognize the sort of bound that this is. And then we also show that the above rate is this bound here, essentially optimal in a certain sense, max optimal. And here are some, so here are the latent positions that are not given to us. All we have is a neighborhood graph, and we only have the adjacency matrix of that. But if we fill in the graph with graph distances and plot them, so we apply classical scaling to embed the point, and that's what we get. So the R here is the connectivity radius. So this is not given to us. Sorry, this is not a tuning parameter. It's constrained by the problem. And you know, it does pretty well, depending on R. And the method that requires convexity is just like the other ones that are based on graph distances. Otherwise, it sort of tries to make things look Euclidean when they're not. Okay, and I think that's it. Thank you very much.